Okay, so I will present Eren to present his paper, Information-Theoretic Guarantees for Recovering Low Symmetric Rank Tensors.
Are you in the mic?
Okay, so the problem is there's a rank T star which is of order L, which means this multiplier of D is multiplied L times, and we want to recover this tensor by these measurements. So the measurement vector xi is a d-dimensional vector, and this is also also a tensor induced by this vector. So we are interested that's in a noiseless setting, and we are interested in the sample complexity for recovering this T star. And we will assume that the rank has the tensor has low symmetrical rank, which means it can be written as a summation of at most R rank-1 tensors. Okay, and we will also assume this, the measurements have log concave entries. It's a random measurement. The major motivation for studying such a problem is that the setting can be closely related to a two-layer polynomial network. So that is to say, if we consider a two-layer neural network, which the activation function is a polynomial to the power L, then if the weights are Wj and the output is averaged by Aj is some real number, then one can write the same write it in the same way by a tensor of order L, and it's as we can say, it's a symmetric symmetric low rank tensor whose rank is at most R. So it includes a two-layer neural network problem with a link function to the polynomial to the power R to power L. So let's first consider the benchmark. If we minimize the symmetric rank of the tensor and the subject to the constraint that the measurement is equal to our data, then what's the sample required to recover such a tensor? And it turns out if the order of the tensor is smaller than some constant, and if I have d times r samples, then the symmetric rank minimization will recover this tensor with probability 1. So this gives an upper bound that the minimal number of samples required is d times r. So it's reasonable because T star has d times r unknown variables, and we need the d times r measurements to recover it. So the proof is based on, so if we assume the estimator is not equal to T star, then define the T delta in this way. So the proof mainly be, proving the following claim. So this set is the tensors whose rank is smaller than 2R, because if we define T delta, then this tensor has rank less than 2R. And it contains two steps. First, we need the covering number on this set, and the next we bound each event by this inequality, and finally apply union bound for all the possible tensor in the epsilon net. Okay, so now let's consider the empirical risk minimization, where we minimize the empirical risk for over the space by symmetric order L tensors. And if we consider the generalization error defined here, then if the samples are bigger than d to the L, then this EIM can recover the ground truth. But if otherwise, the generalization error will be big. So so in this empirical risk minimization, we don't put the constraints that the tensor is low rank. So this is why the sample complexity is worse than the symmetrical minimize the symmetrical rank. Okay, so is there a lower bound for recovering the tensor? So it's I think the answer is yes. So if we basically it's based on a packing number over the set and apply phenotype's lower bound. So one can construct some sets which has size bigger than exponentially d to the r 0.98, such that for each any 2 points in this set, they are separated. And so with this guarantee, then one can show if I sample a tensor uniformly in this set, then with some non-zero probability that the estimator will not equal to the ground truth if the sample size is smaller than d times r to the 0.98. So the 0.98 is can be arbitrarily close to 1. So which means this proof give a lower bound that d times r samples are necessary. And there's a few future questions. So first we compare to the current result. In the other parameter setting, we improve the bounds, and if under some setting assumption on the weights and on the weights of the neural network, our bound also improves a little bit. So in the future, it's so how to solve in the upper bound it's computationally inefficient. Can we provide some method that's running in polynomial time, and we also don't consider the noisy measurements. So yeah, so that's all the results.